All right, so now let's take a look at how we can evaluate this log normal model with these relatively informative priors. So what we fit in the previous lecture was a simple linear model with reaction time as a function of some intercept, which is the mu parameter. We had this spacebar data, which records reaction times in a button pressing task, and we have a log normal likelihood with these priors. Normal distribution, mean 6, standard deviation 1.5 for the mu parameter for the intercept, and a truncated normal with mean 0 and standard deviation 1 for sigma. The truncation is done by BRMS internally because BRMS, the package, knows that sigma cannot have negative values. So the truncation is done internally, right? So once you have the posterior distribution for the mu parameter, for example, typically in a scientific research problem, this is the parameter that we are primarily interested in, right? The sigma is usually a nuisance variable for us. So often there is not much focus on the sigma variable, but what we are interested in is the posterior distribution of the mu parameter given the data. So how would I summarize it? Well, of course you could summarize the posterior in terms of the log on the log scale, but it makes more sense to actually look at the posterior on the millisecond scale here. So you can interpret it in terms that you understand. And so one way that you can do this is to basically just take the exponent of the posterior distribution, right? This entire distribution, just exponentiate it, and this gives you the median, of the posterior. And so what you can then do is you can calculate statistics on this distribution and report the mean and the 95% credible interval. So this information I would report in a paper, if I'm summarizing the results of this analysis, and this tells me pretty much everything I need to know, that given the data and given my priors, my predicted or expected reading time is 167 milliseconds, and I'm 95% sure, given these data, given these particular data, that this ranges between 164 and 169. Of course, this credible interval does not mean that these are the true values of this mu parameter, because these values are conditioned on the data that we happen to get. Maybe we've got skewed data, maybe we've got biased data from a subject who was particularly tired or not representative of their normal behavior on some other day, right? They might not have slept the previous night, for example, right? So it could be biased data, and so if the data are biased, then your estimates are not going to represent the reality. So you should treat all these credible intervals and these means as, you should be very clear about the fact that they're conditioned on the data that you have, right? And whether those data reflect reality or not, who knows, right? So it's tempting to generalize from these data, from these posteriors, to the unknown reality out there. But the reality is by definition unknown. We just don't know what the true mu is. We are trying to get at some estimates of these given some priors and given the data that we happen to have. Okay? All right, but we can still look at the posterior distributions, the posterior predictive distributions, to see if the future data produced by this model is reasonable given the data that we actually have. So this is just a sanity check which tells us that yes, the model is producing reasonably distributed data given what we've seen in this particular data set, right? One other question that one often asks is, well, I had this normal likelihood earlier and then I switched to the log normal likelihood. Did I get an improvement in the fit in some way, right? So you could ask whether the likelihoods are, one likelihood is better than the other likelihood. So that's an interesting question to ask too, and you can use the posterior predictive data to check that. Okay, so here is the distribution of the minimum reading times produced by the normal likelihood model that we had fit long ago, and this vertical bar is the observed minimum reading time. That's of course a point value in the data, right? And so what we notice is that the normal model is actually generating too small minimum reading times here, right? The distribution is too far away from the vertical bar that we've got here, right? in the log normal model, we see a somewhat better distribution of minimum reading times, right, compared to the observed data. So in that sense, subjectively, just looking at these figures, right, intuitively, I don't have any quantified statistics or anything here. I'm just using a graphical check to decide whether the log normal model does better than this normal model. And the answer seems to be yes. I'm producing minimum reading times that are pretty close to the actual observed minimum reading time. Okay. Now one can also check whether the two models, the normal likelihood model and the log normal likelihood model, whether they reflect the maximum observed reading time in the data. So the maximum reading time observed is about, well, it could be about 400 and something milliseconds, right? But the normal model, the maximum reading times are very short, right? So it's kind of missing something important. The normal model is missing something important about the observed data, right? And interestingly, the log normal model is also underestimating the maximum reading time. So if this data is representative, of some kind of systematic behavior of this subject, then both models are actually failing to capture that, right? So often models will be imperfect in this sense. Even the log normal model does not capture all aspects of the data. Often that's okay. Models are always imperfect. That's why it's called a model. It's not the actual reality, right? So they will miss some aspects of reality. You just need to know what those aspects are and what's missing in the data. So in this particular case, what could be happening is that what we might be looking at in the data is not just one distribution, but a mixture of distributions, right? So what could be happening is that when we look at data we see the skew in the data, right? What could lie behind that single distribution that we are seeing is a mixture of two distributions that look like one skewed distribution. So there could be a mixture process that's producing this data. As you will see in the later lectures in the textbook, you can actually define a generative process where you assume that there are a few rare slow reading times that could model this long tail here of very rare but very slow reading times. These could be attentional timeouts that the subject is experiencing, getting bored pressing the button. They could be in rare occasions producing very slow reading times. But most of the data could be coming from a different distribution. So you can actually define these kind of finite mixture models that can model this kind of data. So this is an elaboration of the linear model, right? And this also illustrates the great flexibility of the Bayesian approach. You can really build elaborate process models that reflect the underlying generative process, and it doesn't have to be a simple generative process of the type that we are studying here. That's one of the beauties of the framework that we are looking at here. Okay. All right. So what's happened so far? We've looked at two simple examples of a simple linear model using two different likelihoods, the normal and the log normal. And what we learned to do was to generate prior predictive and posterior predictive data using the BRMS package. We can do that, or we can do it in R ourselves, right? And so these two approaches to understanding the model are very important. They will teach us about what the model predicts and what the underlying assumptions of the model are, right? Whether they make produce reasonable data, right? And so what we tend to say is that these are telling us about the descriptive adequacy of the model, right? And so we can ask both what happens before we've seen the data, that's the prior predictive distribution, and what happens after we've seen the data, that's the posterior predictive distribution. And this is usually part of the workflow of doing a Bayesian data analysis. You do these prior and posterior predictive checks, you do a sensitivity analysis, and that constitutes a complete analysis of data set, right? Usually you may only report the final analysis in the paper, but underlyingly there's all this investigation that one should do to check whether the model makes any sense at all, right? All right, so what's going to happen next is that we are going to now elaborate on this simple linear model in several ways. First, we are going to add a predictor, right? So instead of just having an intercept, we're going to have an intercept and slope, right? And this becomes a regression model. You can also have multiple regression models now. So this improves the flexibility of this linear modeling approach and allows us to ask all kinds of questions about complex data sets, right? Another example I will show you is of using logistic regression. This will be familiar to people doing machine learning, where you've got a 0-1 response, right? Where we're trying to model this kind of Bernoulli process, right, using a linear modeling framework, right? So we're going to use logistic regression for that. And finally, I'm going to show you just a glimpse of what a linear mixed model or a hierarchical model looks like, where you start adding information about individual participants, the variability due to individual participants into the model. This is a very sophisticated framework that allows you to study individual differences, for example, and it allows you to analyze repeated measures of dependent data. This is a very important framework, and it's a bread and butter framework for many fields like psychology and linguistics. So that's coming up next.